数学教授
Hi everyone, welcome to today's video. Today we will discuss the equivalence relations. To start with, imagine that you are given two triangles, and recall that they are congruent to each other if you can put one triangle on top of the other exactly by means of reflection, rotation, and translation. The congruence of triangles is clearly a binary relation on the set of triangles. Yet, it is indeed a very important one, as it enjoys several nice properties. First, each triangle must be congruent to itself. Second, if triangle 1 is congruent to triangle 2, then triangle 2 must also be congruent to triangle 1. Third, if triangle 1 is congruent to triangle 2, and triangle 2 is congruent to triangle 3, then triangle 1 should also be congruent to triangle 3. The generalization of these nice properties are actually used to characterize a very important class of binary relations, namely the equivalence relation. Let's see what it is. Alright, let us first look at the definition of an equivalence relation. Note that an equivalence relation on the set A is a priori a binary relation on the set A. So it has to satisfy every single requirement for a binary relation, yet it is more than a generic binary relation because it has to satisfy some extra properties of its own right. First, the reflexivity, which requires that every single element X in A should be related to itself. Second, the symmetry, which means that whenever X is related to Y, Y should be related to X as well. Third, the transitivity. This requires that X being related to Y and Y being related to Z together imply that X being related to Z. As you can see, these properties are merely generalizations of the properties we just discussed for the congruence of triangles. And needless to say, the congruence of triangles is an equivalence relation on the set of triangles. In the following, we'll define several different binary relations on the set of real numbers, and we'll check if each of them is an equivalence relation or not. In our first example, X being related to Y is defined as their product being positive. This relation is not reflexive. To see this, simply notice that 0 multiplying 0 is equal to 0, which is not positive. Hence, 0 is not related to itself, and the reflexivity fails. How about the symmetry? Well, given any elements X and Y, real numbers, X being related to Y implies that XY is positive. But we know the multiplication of real numbers is commutative. So this in turn implies that YX is also positive. And now by the definition of the binary relation, we see that Y is related to X. So the symmetry actually holds. Concerning the transitivity, for any X, Y, Z real numbers, such that X is related to Y and Y is related to Z. Using the definition of the relation, we see that the first condition means XY is positive, and the second condition means YZ is positive. Now, multiplying these two together, we see that X, Y squared, Z is also positive. Yet Y squared here has to be positive, so that from here, we can see XZ is also positive. Therefore, X is related to Z, and the transitivity holds. To summarize, this relation is symmetric, transitive, but it is not reflexive. As a result, it is not an equivalence relation. Our second example is pretty much similar to the first one, except that this time X being related to Y is defined as their product being non-negative. Well, let's first check the reflexivity. Indeed, for any real number x, we see that x multiplying itself is equal to x squared, which is greater than or equal to 0. Hence, this relation is reflexive. Next, for the symmetry, given any real numbers x, y, such that x is related to y, then it means that xy is non-negative. But again, by the commutativity of the multiplication for real numbers, we see this in turn implies that yx is also non-negative, and from there we conclude that y is related to x. Thus, this relation is also symmetric. Finally, for the transitivity, well, let us pick x to be 1, y to be 0, and z to be negative 1. Let's see what happens under this setting. Clearly, 1 times 0 is equal to 0, which is non-negative. Hence, 1 is related to 0. Similarly, 0 multiplying negative 1 is equal to 0, which is again non-negative, so that 0 is also related to negative 1. Yet, 1 multiplying negative 1 is equal to negative 1, and this is negative. Hence, 1 is not related to negative 1. And you see, unfortunately, the transitivity fails here. Thus, this relation is reflexive, is symmetric, but it is not transitive, and hence not an equivalence relation neither. In our third example, x being related to y is defined as a disjunction of two conditions. More precisely speaking, either y vanishes or the ratio of x and y is at least 1. Well, let's check if this time we got an equivalence relation. To begin with, we look at the reflexivity. Given any real number x, we know that there are two possibilities. Either x is equal to 0, or x is not equal to 0. But if x is not equal to 0, then x can serve as a denominator. And we know x over x is always equal to 1, which is in turn greater than or equal to 1. So summarizing these two scenarios together, we see that either x is equal to 0, or x over x is greater than or equal to 1. And this fits the definition so that we conclude that x is related to itself. So this relation is indeed reflexive. But when it comes to symmetry, we need to be a little bit careful. So to this end, let us pick x to be 2 and y to be 1. And under this setting, we see that 2 over 1 is equal to 2, which is greater than or equal to 1. And from there, we know 2 is related to 1. Nevertheless, 1 over 2 is strictly less than 1. Hence, 1 is not related to 2. As a consequence, the symmetry does not hold. Last but not least, let us check the transitivity. To this end, consider any real number x, y, z such that x is related to y and y is related to z. And now, by the definition, x being related to y means that either y is equal to 0 or x over y is greater than or equal to 1. Similarly, y is related to z so that either z vanishes or y over z is greater than or equal to 1. And we want to check if x is related to z, and to this end we distinguish two cases. So either z is equal to 0, and for the moment we don't do anything. And in the second case, z is not equal to 0. And let's check what happens in this case. So z is not equal to 0, yet y has to be related to z. So that means the second condition must be satisfied. So this implies that y over z is greater than or equal to 1. Yet in particular, this implies y is not equal to 0, but x has to be related to y. So if y is not equal to 0, then x over y should be greater than or equal to 1 as well. Hence, we got these two inequalities, and multiplying them together, we see that x over z is equal to x over y multiplying y over z, as the y terms cancel with each other. That is greater than or equal to 1 multiplying 1 based on the previous two inequalities that we have written here, and that is equal to 1. So, summarize what we got. Either z is equal to 0, or x over z is greater than or equal to 1. But based on the definition, this means precisely that x is related to z, so that this relation is indeed transitive. Now, we see that this relation is reflexive, transitive, yet it is still not an equivalence relation because it is not symmetric. Alright, in our last example, x being related to y is defined as either both of them vanish or their product is positive. As usual, we start with the reflexivity. So given any real number x, we see that there are two cases. Either x is equal to 0, or x is not equal to 0. But then this implies that x multiplying with itself is equal to x squared, and that is strictly positive. So we have shown that either x is equal to x equal to 0, or x multiplying x is greater than 0. And from there, we see that x is related to itself, and this justifies the reflexivity. Now let's check the symmetry. To this end, let x, y be real numbers such that x is related to y. This means by definition that either x and y both vanish, or their product xy is positive. And from there, we can write the first condition as y is equal to x is equal to 0, and the second as yx being positive. But you see, this is precisely the definition of y being related to x, so we conclude that y is related to x. And this justifies the symmetry. Finally, how about the transitivity? Well, for real numbers x, y, z, such that x is related to y and y is related to z, the first condition reads either x and y both vanish or xy is strictly positive. And the second condition reads either y and z both vanish or yz is positive. And now we got to check if x is related to z, and we will distinguish between two cases. In the first case, we have y is equal to 0. If y is equal to 0, then you see that for x to be related to y and y to be related to z, the second part will no longer hold. So we really need the first part to hold. But then it means that x is equal to z, that is equal to 0. So x and z both vanish. And the second scenario, where y is not equal to 0. So similarly as before, now for x to be related to y and y to be related to z, you see the first part can no longer hold. And that's why we need the second part to hold respectively. As a result, this means that xy is positive and yz is also positive. But then, using a similar argument as in the previous example, we see that xz should be positive. So now let's summarize these two cases. We see that we have actually shown that either x and z both vanish, or xz is positive. And now, based on the definition, we have shown that x is related to z, and hence the transitivity. Now we see that this relation is reflexive, symmetric, and transitive. As a result, this is indeed an equivalence relation. Alright, hopefully today's section gives you a general idea what is an equivalence relation. In the coming section, we will use equivalence relations to regroup elements of the set into different classes, namely the equivalence classes.